Okay, hello and welcome everyone. So this is a re-recording of an Ethereum engineering group meetup that we had some months ago, which unfortunately the recording didn't go so well for. So it's an introduction to Ethereum aimed at engineering people. And I've got Trent and Adrian on the line. And Trent and Adrian are going to ask tricky questions whenever they feel the need to, which will help simulate an audience, because I think a presentation with an audience always works so much better. Yeah. Okay. So this presentation will give you a background on blockchain technology, and really, I think explaining Bitcoin first helps you understand Ethereum. And I'm assuming that you've got some general engineering background. And, we're going to walk through from just blockchain and distributed ledger, talk about Bitcoin, talk about Ethereum, and then, just a sec, just quickly checking something. Yep. We're going to talk about Ethereum, talk about smart contracts, and just walk it through. So, distributed ledgers, they're essentially a distributed database whose contents are agreed upon by nodes or entities who don't really trust each other. And so it's a cryptographically linked list of authenticated transactions. So you've got to sign a transaction and then it gets added to a linked list that's cryptographically tied together. And so the transactions are grouped into blocks, and all the transactions on the blockchain can be applied in order. Let's fix that whilst we're here. Can be applied in order to yield the current state of the distributed ledger. So the sum of all the transactions equals the current state of the ledger. And so, you can imagine you've got a whole stack of nodes. And so a user introduces a transaction into the network on a node, and then peer-to-peer communications happens that propagates the transaction across the network. And so when you're thinking about these sorts of networks, you've got to think about decentralization, and decentralization's core to Ethereum. And so you've got architectural decentralization, and that's where you've got, say, a fault-tolerant system. There's no centralization point, no single point of failure. And so if a network connection breaks or a server blows up, yes, the network still works. Political decentralization is about you don't want to have one single entity or person controlling stuff. So you want to have a group of people or many people controlling the network, and not just one or two. Logical decentralization is about the ability to have inconsistency within an internal state. And so you can imagine, like, if we had in a blockchain, you want to have a logical centralization where you have one agreed state, whereas, say, in English, we have decentralization, and say the word colour can be spelt with a U or not with a U, depending on where you live. And so that's a logical decentralization of two ideas for the same concept. And so greater decentralization leads to greater network resilience. And blockchains need to have architectural and political decentralization, but not logical decentralization. So you want to have an agreed state. And so consensus is the process by which you get to an agreed state. And it's essentially what blocks are valid, or what groups of transactions are valid. And so proof of work is a way you can do that. And so you have a whole stack of computers, like in those two pictures there, somewhere where the electricity is cheap, and you solve a puzzle problem. And essentially by solving that puzzle problem, that's the act of solving it is the mining that you hear about. And so the puzzle is hard to solve, but really easy to verify. And so lots of different blockchains like Bitcoin and Ethereum use proof of work at the moment. But proof of work's a massive waste of electricity. And so proof of stake is one possible alternative which doesn't use up tons of electricity. And so you've got a list of validators, and any entity which holds some ether can be a validator. And so you register and you put up your stake, and then you can be one of the validators. And you've got to use some sort of fairness mechanism amongst the validators to work out which validator pops out the next block. And so the idea is that proof of stake should give you a reduced amount of centralization. So at the moment with proof of work, there are only between 2 or 3 big miners. You've got more than 50% of the network on Ethereum. So there is actually a fair bit of centralization in mining pools at the moment. So this would give you more centralization, energy efficiency for sure. It'll be less power being used, and security. The thought is that it should improve the security overall. I encourage you to read the proof of stake FAQ. Proof of authority is another a system where you have trusted nodes. So you can't, proof of stake and proof of work allow you to have untrusted nodes, where proof of authority relies on all the nodes being to an extent trusted. And so the reputation attached to each validator's identity really is the big thing for this. So assuming that you want to keep a good reputation, you've got to be a good validator, and hence that's what this system relies on. So another thing to think about is crypto economics. So the short version is that you want to incentivize good behavior and disincentivize bad behavior. And so it's about trying to work out, are we incentivizing the right thing? So for a peer-to-peer system, is there any incentivization to forward a packet? Or why should a miner, mine some transaction? And so whenever you're thinking about designing a new protocol or a new algorithm, you've got to be thinking about the crypto economics of it. Will it make sense? Will people do this? And one thing that I've heard people say is it's just economics. It's, nothing fancy really. So Bitcoin identifies everyone using an ECDSA P256 key pair. So everyone's identified by essentially the hash of the public key. And so each transaction has one or more inputs and one or more outputs. And so these are these UXTO, so unspent transaction output transactions. And so each input contains a source identifier, so a hash of the previous transaction and a signature. And then the output contains the hash of the public key of the recipient and the amount to send. And so within Bitcoin, there's a scripting language, a primitive one, but there's a scripting language. And so all the transactions are actually scripted in a programming language, which is stack-based. So there's no looping. And so there's a large variety of instructions which could allow for a complex language, but 99.9% of all scripts are exactly the same script, which does a simple transaction. And in fact, miners are unlikely to want to mine anything that's not one of these standard transactions. And so with this standard transaction, you've got essentially the input is that, those 3 pieces, and then the output is that. So working that through, you can imagine you've got a stack which is empty, then you have all of that is the script. And then what you do is you push the public key signature and the public key onto the stack, and then the op duplicates the public key. Then you hash the top of the stack, which gives you the hash, and then you push the other hash on, and then you say, is the other 2 hashes at the top of, or 2 values at the top of the stack equal? So if they are, then what you do is you check the signature of the public key with the signature, and if they are, then you can say the transaction's good and it's good to go and it's gone through. And that is how most Bitcoin transactions operate, is by that simple script. So there are a few issues though, and so one was that the miners are going to reject pretty much anything that's not a standard script. Bitcoin only allows for 1 megabyte of transactions per block, and so that means that you're limited in the number of transactions per second to only about 7. And so if you had longer scripts that did more interesting stuff, you'd be reducing the number of transactions. And also some of the instructions are disabled because of bugs in them. So they haven't been used for years. There's no looping. And if you wanted to add any new instructions, it's going to be a soft fork. So yeah. And another thing is you don't have per contract state. There is no real state for a contract. It's all just global state. So Bitcoin, all the transactions are put together into Merkle trees. So Merkle tree is that hashing that you've got there, where you've got the hash of each transaction. The two hashes are pushed together in another hash, and then you have essentially a root hash that is in the block. And then you have a hash of the previous transaction. So in that way, you're linking all of the transactions with the previous transactions that have happened in the past. And so that's how the overall transactions are merged together in Bitcoin. And then there's a block header. The block header has some interesting information. So it's got the version, and it's got that previous block hash, the Merkle root of all the transactions, the time that the block is being mined, and then the target, which I believe is essentially related to the proof of work. So that's the how hard the algorithm is to solve, and the nonce, which is the nonce value that you need to use to get to the right or below that target value. Okay, are there any questions about general blockchain or Bitcoin?
I think I'm good.
Okay, cool. All right, Ethereum. So Ethereum is a blockchain which supports, in inverted commas, a Turing-complete programming language with an effective unlimited intertransaction storage capability. So, big words, but Turing-complete programming language would imply it could do anything. However, you're going to need to use gas, and gas to store stuff, gas to execute instructions, and there's a limited amount of gas that can be used per block, because you can only do so much in a block, and so you can't do anything. You can only do quite small programs. And so Ethereum's aim to build on Bitcoin's ability to facilitate transactions between individuals who wouldn't otherwise have means to trust one another, and provide this blockchain-based computation platform for general solutions. So there are some very application-specific blockchains, whereas Ethereum's aiming to be a general-purpose blockchain to give you general-purpose solutions. And so it has this executable code called smart contracts, which sit in the distributed ledger. And so you've got the code and the data, and the code's executed by an Ethereum virtual machine. And so you have some high-level language code like Solidity that gets compiled down to bytecode, and the bytecode's the thing that actually gets executed in the EVM. So you've got transactions, and so you've got one transaction might be to deploy a contract, another one might be to call a function on a contract, or maybe to transfer Ether from one account to another. So Ether is the raw unit of value in Ethereum. And so 1 Ether equals 10 to the 18 WE, and which was about $880 back in mid-February. And so the idea is that each line of code that's compiled into an opcode costs some gas to execute, and different operations cost different amounts of gas. And so you buy gas at a floating amount of WE for each transaction. So you say, hey, I'm prepared to pay this amount of gas to get my transaction executed. What do you say? And then someone might say, yes, I'll mine your transaction based on that gas price. Or maybe they won't. Maybe you'll have to pay more. So miners choose which transactions to accept based on the gas price and based on how many people are submitting transactions. And so, you know, as well, you've got a gas limit that you specify, which essentially says how much gas and how much ether am I prepared to pay to have this transaction executed, because maybe there might be looping, so you might not know exactly how much ether you're going to spend. So this will give you an upper limit. So currently gas costs between 0.2 and 50 gigaWi, so which is written as GWi. And so there is a market for transaction processing. So if you have a look at this gasstation.info, you can see what the current gas prices are and what gas price transactions were mined at recently. So I think the upshot appears to be that if you're prepared to pay a high gas price, chances are you will get mined in the next block. If you only want to pay a little bit of gas, or maybe below market rate, then you might have to wait a few minutes for your transaction to be executed, but you might be able to pay an order of magnitude or 2 orders of magnitude less gas, or less ether, to have exactly the same transaction mined. So, it really depends on how quickly you need things mined. So this is a list of transactions and the gas cost. And as you can see, the gas cost is wildly varying. And so actually storing bytes, or 32 bytes onto the blockchain is enormously expensive. And creating a contract, again, is enormously expensive. Whereas maybe just doing some small instruction might not be that much at all. So it really does come down to what you're doing. And the idea is that people have tried to match the economic cost of running a transaction or running an instruction with the actual real world cost to prevent attacks. And so the values have changed over time. And because people were exploiting differences between the actual gas price and the real world cost to essentially do denial of service attacks. So if you look at this contract creation, 53,000 gigaWi, then actually no, there's 53,000 gas, should I say, and assuming a 10 gigaWi gas price, then it would cost about US 46 cents to execute this instruction. But you've got to think, though, to launch a contract, in addition to this price, you're going to need to pay for running the constructor plus storing the code and data onto the blockchain. So it can be quite expensive. In Ethereum, there are 2 types of accounts. There are externally owned accounts and contract accounts. So externally owned accounts are ones that, you've got a key pair, and they're the ones that can trigger a transaction. Whereas a smart contract is, it's an account at a certain address, and the address is the account address. It can be the recipient of transactions and can then create do more function calls based on it, but it cannot trigger a transaction. Both types of accounts can actually hold ether, though. So miners, they run transactions in the EVM and they come to consensus on proof of work, which was that time-hard memory problem, problem. And so they get money or get ether from executing the transactions and being the first person or first entity to come up with the proof of work, or the solution to the puzzle problem. Which is what I'm just saying here. So the block reward, the cost of executing the instructions, and also there's something called uncles. So that you can imagine that another Ethereum miner node has come up with a solution to the puzzle problem, and has a set of transactions which are ready to go, and it's worked out a good. And if those transactions don't intersect with transactions on what's now the main line, then that what's called uncle block can be incorporated into the overall system. And the miner who incorporates it in gets some percentage of their the gas fees or the ether from that. So smart contracts is, the code that sits on the blockchain. And so there are a variety of languages, but Solidity is by far the most popular one. And so the syntax is a bit like JavaScript and Python. And there are other languages, and, Viper's an experimental new one, which might be helpful. But, Solidity is the main game. It's the most popular. There are tools, and they're getting better and better all the time. But the maturity is nowhere near, say, a language like Java. So in Solidity, contracts, you can sort of think of them as classes. It's statically typed. There are structs, interfaces, and you've got inheritance. You've got cryptographic operations and blockchain-specific operations. And there are all sorts of libraries out there too that come with it. And so if you look at some Solidity code, you've got a version number at the top, which is the version of the language that you're looking at. Contract greeter, so that's a bit like, the class, saying it's a class. You've got a few variables, and one of the variable types is an address. So this actual Solidity code's a little old now, because now this function greeter, which matches, the name of the class or the contract, is now replaced with something where you would write constructor to indicate that this is the constructor. And then you have a parameter that's going to come in. You're saying it's public, and your then a message sender is a special sort of variable, which is which entity sent this transaction. So who instigated the transaction? And then you're assigning, the variables. You've got a view here. So a view is a special sort of transaction or function rather, where to execute this function, you don't need to mine the transaction. And in fact, you don't have a transaction, because the idea is all the information that's being used there is available in the distributed ledger. So if you've got a copy of the state of the ledger, you could just execute this function, greet, and you're going to get that string value back out. Get block number, it needs to be mined, because this one here is getting the block number. And so that has no context if you were just in the distributed ledger. Set greeting needs to be mined as well. Actually, I've indicated that that's a view and that's wrong. I'll fix that whilst I'm here. Yeah, sorry guys. Yeah, so this cannot be a view function, because if you did run it as a view or tried to compile it, it would give you an error, because it would say, well, block number is not something you're going to be able to access from a view function. Set greeting has to be mined as well. It's another transaction. Yeah, actually, exercise for the reader is to look at how this would actually work, because when you mine a transaction, you don't get a return value. So you'll notice that the transactions don't have return values, but this one does. So my example is broken. And how's that? No one has pointed this out before, isn't it? And I've given this presentation quite a few times. No one's obviously executed the Solidity code and realized that go and get block number is not going to give you anything, because if you mine it, it's not going to give you anything. And if you treat it as if it's a view function, it's not going to work either. So yeah, which just goes to show you Solidity is quite complicated. But now my example fits on the screen, so it's oh so much better. Okay, so greet can be run off the distributed ledger. Set greeting, it has to be mined as a transaction. It's setting state. And then we've got this kill function, which does if the person or entity sending this transaction is the same as creator, which we set up there, then self-destruct and wipe out the contract. So having a self-destruct is actually a really dangerous thing. And this is where the Parity wallet came unstuck, because a self-destruct got called on that, or part of that contract. Yeah. Yeah. So, yeah, as it says here, be careful of, another thing you can see here is that I'm passing in a string. And so if you're passing in a string, then that's variable length. And so you're not going to know. So if this was available via some web application and your users are going to do this and you're going to pay for the gas, then they could make that string really large, which would then mean that you'd burn a lot of gas and burn a lot of ether. And yeah, be really careful about things like self-destruct, because that could cause unintended consequences. So there are 5 types of functions in Solidity. There's the constructor, and that gets run as part of when you're deploying a contract, and you can use it to set up initial values. Once it's run, that code doesn't actually end up on the blockchain because it's never going to be run again. So it's no point having it on the blockchain. You've got other non-constant functions, and so they're ones which are essentially a transaction. And so the parameters that you pass in and the function you're calling become part of the transaction, and you update state variables. View functions, they don't update any state, they're relying on the distributed ledger. Pure functions don't actually use any state at all, and so they're not a transaction either. And then you've got constant functions, and they're a combination of view and pure. And so they were what they were before. So it's deprecated. And you probably find I changed my example without recompiling it, and it was probably a constant function in the past. And the problem with constant functions is they didn't have good error checking, say to check that you weren't doing something that just wasn't going to work. So data, only the contracts themselves can write data to their contract. So no one else, no other things outside of the contract can write. So there are some complexities with Solidity. The programming language, initially it wasn't well designed, and I think there are a few issues with it. That said, it has changed over time. So you want to watch out though if you're copying code from Stack Overflow or somewhere like that, because your example that you might copy from the past may no longer be relevant, or might be not compiled properly. So contracts are immutable, so you're not allowed to change them. So if you want to upgrade, you've got to have a new instance of the contract and somehow or other be able to suck the data out, or maybe you've got the contract set up so you've got a business logic contract which you're upgrading, and the data contract is a separate thing that gets pointed to that doesn't hopefully need to be upgraded. But upgrade's a problem. And obviously code and data is public. So if you've got any bugs in your code, then everyone can see your code and they can immediately exploit your code.
So Peter, just quickly.
Yep.
Is the bytecode decompilable?
Yes, all bytecode is decompilable. Otherwise, how would the virtual that's interpreting it be able to execute it?
Sure. Crazy question.
Yeah, so you could obfuscate it, you could do all sorts of things, but yeah, even in the good old days before there were good decompilers, you could use your eyes to look at the opcodes that are being put there and use your eyeballs, as it were, eyeball debug, and just light up what the code was doing. But now there are debuggers or disassemblers. So yeah, you've got to assume that your code is
public.
Yeah. Okay, so we've talked about Ethereum, but how does it link to, say, an application? So this is my take on it, and everyone throws stones at me and say I'm wrong, please, or give ideas on how we can improve this. But I think this is centralized but decentralized. And so, you've got some mobile phones there that have got some sort of app on them. They're talking to a reverse proxy, which is front end, Rabbit back end, and maybe maybe you've notification services back to the phone. So that's not actually that different to a normal app. And then you've got, say, Infura or some other gateway, or maybe you host the Ethereum nodes yourself, and you talk to via some gateway to the Ethereum network to your smart contract, and maybe you use the Ethereum name service to point at your contract, so you can use a name rather than the actual address. And maybe you use something like IPFS for your distributed file system. And maybe your users, in addition to accessing the whole thing this way, maybe they access the Ethereum network directly and have, say, Ether in their accounts. And so maybe they're paying for something via Ether. So this style of application is quite common at the moment. If you look at applications that are using Ethereum, it's quite common that the Ethereum is really just being used as a micropayment service or some other small thing, and all the big thing happens in a relatively centralized set of cloud services. But you can imagine that over time, this sort of system would change, and you might end up with a more decentralized style application. But this is generally how things fit together at the moment. So the next part I'm going to hit is around Etherium clients. So you've got the Ethereum blockchain is run using, amongst Ethereum nodes, and those Ethereum nodes run software, and that software is, Ethereum client software. And so at the moment, there are two main ones that are actually used, Geth, which is written in Golang, and Parity, which is written in Rust. And the Pegasus team at Consensus are creating Pantheon, which is written in Java. And so an Ethereum client looks a little bit like this. This is what the architecture looks a little bit like. And so you've got, say, the RPC is the interface through which you communicate with the client. And you've got some storage off to the left there, and the storage holds the state of the blockchain. And so you've got code is kept separate from your data, and so that's your world state. And then you've got your wallet, which you could choose to have a wallet within your Ethereum client, and that might hold your keys. Then you've got your Ethereum core. And so you've got your consensus algorithm, so how you work out what's the next block, synchronizer, which is sending transactions, and you've got your transaction pool, which is just a list of transactions that your client knows about. You've got your block validator, which validates blocks and blocks of transactions, which is what the block processor, transaction processor, and bytecode executor do. And then you've got your networking, which has got a whole lot of protocols and sub-protocols that you use to communicate with other nodes. So, yeah, the RPC is the main API for accessing an Ethereum node. And in the network, we've got the discovery, and that's finding other nodes on the network, and starts off with some boot nodes, which are hard-coded, and then finds what peers they're connected to, and based on a reputation system, works out the nodes to connect to. And you've got sub-protocol negotiation, so you work out what messages can be handled by the attached peers, and then you determine common protocols. And then you've got the Ethwire protocol, which is how you do all the Ethereum mining and transaction sharing. And then you've got, say, Whisper, which is a communications protocol for sending messages outside of the blockchain. And Swarm is a distributed file system, a bit like IPFS. So the Ethereum client architecture. So we talked about the transaction pool as being, the candidate transactions that could be put into a block or will be forwarded to other nodes. Synchronizer synchronizes transactions. Consensus, how do we work out what is the next block? And the block validator, let's validate the blocks that we're receiving from other nodes. The EVM's executing the instructions. The bytecode executor executes the bytecodes, which is in the transaction, and gets code out of code storage. Transaction processing is executing individual transactions and updates the intertransaction state. And then the block processor, manages essentially the sequential execution of transactions within a block. And then we've talked about the blocks, the storage. So we've got the blockchain is the block headers. The world state holds the distributed ledger in what's called a Merkle-Patricia tree. So it's similar to a Merkle tree, but it also has some data organization on top as well. And that points into the code storage and account storage, and the account state rather. An account state is holds the data for the contract accounts and the externally owned accounts. And then you've got
Patricia typo. Needs another I after the C.
Does it? Let's have a look. Patricia. Thank you. Thank you. Okay. All right. And then we've talked about our wallet. Thank you. Okay. So there are 4 types of Ethereum nodes at the moment, Ethereum clients. You've got a light client, which can receive blocks, validate, and send transactions using a subset of the world state. You've got a full node, which is the light client plus it can verify blocks that are broadcast onto the network, holds the current state, current world state, and holds the entire blockchain of block headers. So then you've got this full archive node, and it holds the previous world state in addition to the current world state. And then you've got the mining pool lead, which does everything that the full node does, plus it actually does the mining and participates in consensus. So it's the thing that can knock out the new blocks. So though you've got all these different types of nodes, they all can run the same software, they're just configured differently. So this, I think, the next section really talks to, so if you have a transaction come into the network, how does it happen? How does it end up on the distributed ledger? And so in my example, we've got a whole lot of different types of nodes. So you've got an app, which has got some local key storage, which is talking to a light client, and then that's on the network. Then you've got an app with local key storage, which talks to a full node, which is then on the network. And then you've got a light client that you might have. And so let's walk through how do we actually go from here. So we've got to remember this is our Etherium client. And so, so the application with the local key storage, so that was the first one. The user interacts with the API in the application, and it creates a candidate transaction, signs it with its private key, and communicates it to the light client via RPC. The light client's going to put the transaction into its synchronizer, and then it's going to use the ETH-wire protocol to distribute the transaction across all the connected nodes. Then you've got the other one was the Etherium client, this one here, which is connected to the full node. And so it interacts, user interacts with the application, you create a signed transaction, you communicate it to the full node. The full node can verify the transaction. So the light client couldn't, but the full node can. And it puts the transaction into the transaction pool, and then they're communicated to the synchronizer using the wire protocol, communicated from the synchronizer using the wire protocol to all the other nodes on the network. And it's in the transaction pool for that node. The light client, so it's, via RPC, it's going to, so this is the example C up here. So it gets the transaction, out of secure account storage, it gets the key, signs the transaction, and puts the transaction into its synchronizer, gets shared across the network using the Ethwire protocol. So the transaction gets flooded across the network. So all transactions go everywhere across the network. And so all the full archiving nodes, the full nodes and the mining leads will have a list of candidate transactions in their transaction pools. And then the mining lead is going to review its transaction pool, and it's going to pick the transactions which are prepared to pay the most gas, or maybe it'll have a threshold that it's not prepared to accept below. And then it'll put the candidate transactions that it wants to have in its candidate block, and then it'll start trying to solve the proof of work problem. So that's not actually going to happen on the same computer. I imagine then that's where you've got the huge farm of those computers that is working on the proof of work problem and trying to find that nonce to solve the problem. And they'll have their own Coinbase transaction in there as well. And so assuming they find it, then they'll distribute that block across the network using their synchronizer. And I know if I was a mining pool lead, I would make sure that that block goes to the other nodes that are doing the other miners as quickly as possible, because you want to tell the other miners, hey, I'm ahead of you, you should use my block. So the full nodes and archive nodes check the block using their block validators and then add the block to their blockchain in world state. And then light clients, they can request information about the estate, or rather about the account state for a certain account. And so calls to any of the nodes now should show the results of the transaction. Though for how Ethereum works though is if you want to do a get, so any view type of function, you are viewing from 6 blocks back from the current. And the reason for that is that you want to be getting stuff that is guaranteed not to be rolled back. And 6 blocks is deemed to be probabilistically quite secure. So the next, I've got a few slides about Consensus, but yeah, Consensus is the company that I work for. Venture production studio, we do lots of things. And in particular, for those people watching from Australia, we've got people in Australia. And there's Protocol Engineering Group is the group I work for. Additionally, if you live in Brisbane, you should consider coming along to the Ethereum Engineering Group meetup, which we have lots of people come along, and we have a live stream as well. So if you're not in Brisbane, you can watch the live stream. So distributed ledger is essentially a distributed database whose state is agreed upon by entities who don't trust each other. Ethereum is all about decentralization, and you should keep thinking about that when you're designing parts of the overall system or using it. So creating good decentralized applications really relies on knowledge of the platform. And if you don't understand the platform, then I think that you're risking not having a good DApp. So understanding the clients and the overall system is something that's interesting. Oh, and of course, Consensus is hiring. So, please keep that in mind too. So are there any questions? Adrian.
Good.
Yeah, I think we failed you as an audience, Peter.
No. Look, thank you guys for listening, and thank you everyone who sees this, the recording on YouTube. I'll stop sharing now.